A year ago, the coding agent question was simple: which one should you use? Anthropic's Claude coding agent, Codex, Cursor, Open Code, a local model in a terminal, pick one, give it a task, review the diff, and hope it did not make a mess. But serious agent work is already moving past that. One agent might be good at exploring a codebase. Another is cheaper for mechanical edits. Another is better at tests. Another can drive a browser. Another runs locally, so you trust it with private context. Another is expensive, but useful for review. So the real question is shifting. It is not only which agent is smartest, it is what system manages all of them. That system is the meta harness, the control plane around multiple agents, or, in plainer language, an operating system for AI agents. And once agents can edit files, run shell commands, open browsers, spend API money, and create pull requests, that operating layer matters a lot. The coding agent ecosystem is fragmenting in the normal way a young tooling market fragments. There are agent command line interfaces, IDE agents, browser agents, repo agents, local model agents, cloud agents, reviewers, implementers, and workflow-specific assistants. That variety is useful, but it creates a production problem. Each tool has different assumptions about context, permissions, memory, logging, and side effects. One agent wants a prompt pasted into a terminal, another wants instructions in Markdown, another keeps state in its own project directory, another uses browser automation, another exposes MCP tools, another has great output, but poor traceability. Manually switching between them works for experiments. It gets brittle as a workflow. You lose comparability because each agent saw different context. You lose reproducibility because each agent changed files in a different workspace. You lose safety because every tool has a different permission model. And you lose observability because the record of what happened is scattered across chat logs, shells, browser tabs, Git diffs, and memory. That is the harness problem. When workers multiply, the bottleneck moves to scheduling, isolation, policy, and monitoring. A meta-harness is not just a group chat for agents. The useful definition is more infrastructural. A meta-harness takes a task, prepares it for execution, chooses or coordinates agents, gives them controlled access to tools, records what they do, evaluates the result, and hands the work back to a human or pipeline. That means it needs several layers. First, agent adapters. A common way to talk to Anthropic's Claude coding agent, Codex, Cursor, Open Code, Hermes, browser agents, local agents, and custom agents. Second, task admission. Before work starts, the system should know the scope, success criteria, constraints, files, commands, and approval gates. Third, routing. Some tasks should go to a cheap model, some to a code-specialized agent, some to a reviewer, some to a browser-capable worker, some to a local model because the context is private. Fourth, isolation. The agent should work in a branch, work tree, container, or sandbox. If it breaks something, the blast radius should be small. Fifth, policy. The harness should mediate file changes, shell commands, network calls, browser actions, secrets, GitHub operations, and deployment steps. Sixth, evaluation and review. Run tests, compare diffs, ask another agent to critique the result, check whether the task actually satisfies the requirements. And seventh, observability. Logs, token costs, commands, patches, tool calls, artifacts, and the final decision trail. That is why agent operating system is a useful analogy. Not literally a kernel, but a layer that owns lifecycle, permissions, scheduling, memory, and input and output around agent workers. The topic database entry that triggered this video pointed at a recent cluster of open-source projects: Omnigent, Loop Engineering, Vercel Eve, Agentlas OS, BrowserSkill, and Ponytail. They are not all the same thing. That distinction matters. Omnigent is the cleanest meta-harness example. Its README describes a common orchestration layer over Anthropic's Claude coding agent, Codex, Cursor, Open Code, Hermes, Pi, and custom agents. It emphasizes supervising multiple agents, switching or combining harnesses, policy enforcement, sandboxing, collaboration, and sessions that can follow you across devices. Loop engineering is more about repeatable agent loops, audit, initialization, cost tracking, synchronization, context management, MCP integration, and work trees. The signal there is that people are engineering the loop around the agent, not just the prompt inside it. Vercel Eve points at durable agent projects, instructions, tools, skills, channels, and schedules live in conventional file system locations. That makes agents more inspectable and operable as software. Agentlas OS uses a specialist agent hub and temporary orchestrator model. BrowserSkill focuses on controlled browser side effects for shell-capable agents. Ponytail is different again, more like a packaged behavior pattern for making agents write less code. It is viral, but I would treat the benchmark claims cautiously. The important point is not that one repo has already won. The important point is that all of them orbit the same shift. The agent is becoming a component, and the system around the agent is becoming the product. Once you have more than one agent, you need routing. At first, routing sounds simple. Send easy work to the cheap model. Send hard work to the expensive model. Use the browser agent for browser tasks. Use the code agent for patches. But agentic workflows make routing harder than that. A normal model router can choose per call. This prompt goes to model A. That prompt goes to model B. Agent tasks are longer. A coding task might include reading files, making a plan, editing code, running tests, debugging failures, and producing a final diff. The quality signal arrives at the end. If the task failed, which decision caused the failure? The model that explored the repo? The one that wrote the patch? The one that debugged tests? The reviewer? That is why the trace router paper is relevant. It argues that agentic routing should align with the task, because the supervision signal is often delayed until the final outcome. Its framework roots at task admission and updates based on terminal reward. You do not need that exact method to take the production lesson. A harness needs task-level accounting, cost per task, latency per task, success per task, and failure mode per task, not just tokens per API call. Otherwise, you can make every individual call cheaper while making the overall workflow worse. Memory is another reason this layer matters. Useful agents are not stateless prompt response tools. They remember project conventions, failed approaches, test commands, architecture constraints, user preferences, and task history. But memory is not free. The Agent KV Shift paper looks at agentic memory systems where retrieved memory units are structured with summaries, keywords, and tags. Pulling those memories into context repeatedly creates prefill and KV cache costs across long interactions. The paper proposes a cache reuse method and reports meaningful prefill speedups in its evaluation. For this video, the exact method is less important than the systems point. Long-running agents create infrastructure problems. Memory retrieval, context construction, cache reuse, latency, cost, and accuracy all interact. A weak harness treats memory as paste more context. A better harness treats memory as a managed system. What gets stored, what gets retrieved, how it is summarized, how it is validated, how expensive it is to reuse, and when it should be ignored. Long context is capacity. Agent memory is operations. The reason to be skeptical about meta-harnesses is that they sit close to dangerous surfaces. A harness may touch your repo, shell, browser, credentials, issue tracker, CI system, cloud account, package manager, and deployment path. That is a lot of authority. So the right evaluation questions are boring and practical. Can it isolate work in a disposable environment? Can it show exactly what changed? Can it block external actions until a human approves them? Can it prevent secrets from leaking into the wrong tool? Can it record browser actions and shell commands? Can it summarize the trace when something fails? Can it compare two agents on the same task with the same context? Can it downgrade gracefully when an API key expires, a model fails, or a tool hangs? The flashy demo is one agent handing work to another. The production version is policies, permissions, audit logs, test gates, cost accounting, rollback, and human review. Individual agents will keep changing. Today, one model is best at code-based search. Tomorrow, another is better at debugging. Next month, a better browser agent appears. Then, a local model becomes good enough for cheap review. Then, pricing changes. If your workflow is tied to one agent, every shift forces you to rebuild the workflow. But if the agent is a worker behind a harness, the durable layer is different. The durable layer is task admission, routing, sandboxing, policy, memory, evaluation, logging, and review. So when you see a new meta harness repo, do not only ask whether the demo looks cool, ask what it controls, ask what it records, ask how it routes, ask how it limits damage, ask how it knows the task is done. Because the next step in AI coding may not be one agent that does everything. It may be the operating system that lets many imperfect agents do useful work without turning your repo into a crime scene.